This is Mr. Collier, and welcome to my first ever video notes. So far in class, we've been talking about, in the last week, acceleration. And we explored it with the Wheel on Ramp Lab. And now we're going to get into the calculation of acceleration. So let's take notes. And the first thing we should do is title this page, Acceleration. Acceleration. And like I so often want to do, is I want to start off with some definition. So let's go all the way over to the left against the red line and write acceleration. And we'll say acceleration is the rate at which velocity changes. The rate at which velocity changes. And we know that velocity is speed in a given direction, so acceleration can be three things. It can be speeding up, an example of that might be if you hit a baseball. That makes that ball increase its speed. It can be slowing down. And that example of that might be catching a baseball. So you definitely, as that ball's flying through the air and gets to the mitt, it's slowing down for sure. And the third one, the one that sometimes people don't think of, is acceleration is changing direction. And an example of that would be maybe a car driving in a circle. Car driving in a circle is continually accelerating. So those are the three things. Acceleration is a change in velocity, and velocity is speed in a given direction. So acceleration is speeding up, slowing down, and changing direction. And for most of these notes, what we're really going to be focused on is the slowing down and speeding up and calculating, quantifying the acceleration. So let's get a formula. The formula is acceleration, and this is a big word I got to spell over and over again, equals speed final. So we're going to say final speed, subtract initial speed, and that's all divided by the time it takes. So if you think about this, if I wanted to know the acceleration of a car, I would say if it was accelerating from stop to getting on the freeway, initial speed would be 0, and its final speed might be 60 miles an hour as you're getting on the Highway 60 or the 202, and I want to know how long that took. So that would be the acceleration. But of course, that's way too long to write it that way all the time. So we're going to write it acceleration equals speed final, S sub f, minus speed initial, S sub I, divided by the time that all took. And another thing I have to throw in here, just so you know, this is a completely new thing, is that we sometimes talk about SI units, System International. I don't speak French, but that's what it is. This equals System International. Which really is just another way of saying the metric system. And we'll talk about that because we're going to want to know about the SI units. So the SI units for acceleration is that big word again, are meters per second, or we can write it meters per second squared. And I won't do it here, but if you catch me in class, I'd be happy to show you the math, how we go from meters per second to meters per second squared. So now let's do some examples. So let's do an example of a roller coaster, because I love roller coasters. And who doesn't? And so let's talk about one. Let's say that the roller coaster, its initial speed, or S sub I, is 4 meters a second. Its final speed, or S sub F, is equal to 22 meters a second. So it sped up quite a bit, and it did all of that in 3 seconds. So let's do the calculation. So let's write it all out. I'm going to write it across to save a little bit of room. But here we go. Acceleration equals S sub F, speed final, minus speed initial, S sub I, divided by the time that it took. If we use the numbers from the example, that will be 22 meters a second is our speed final. And we'll subtract away from that the speed initial, which is 4 meters per second. And we're going to divide all of that by 3 seconds. That equals 18 meters per second divided by 3 seconds. And when we do the math, that is 6 meters per second, or meters per second squared. Now, when you write that for me, you don't have to write both meters per second and meters per second squared. I just want to show you right here what it looks like. Last thing, before these notes are done, I want to show you what that might look like on a velocity time graph. Now, we haven't really talked about this yet, but this is their first exposure, so go ahead and put this in your notes, and when we start talking about it, it will make more sense. All right, so this one, instead of being positioned on the y-axis of velocity, time is still here, and so we're going to show a curve like this, another curve like that. We're going to show it going down, and then speed going back that way. And we're going to label each of these segments. This is segment A, segment B, and this little one right there is segment C. So let's just label them so we have them in our notes. A equals something speeding up. B equals a constant speed or velocity, meaning it's going at 60 miles an hour and not changing. And C equals decreasing speed. Now, when you come into class, we'll have lots of practice doing the calculations, and in the days to come, we'll have practice with the graphs and the interpretation of both position versus time graphs, as well as this brand new one, the velocity time graph. Thank you so much. Please feel free to back it up and listen again.